Hey there, cosmic listeners. Welcome back to the channel, or welcome if you're new here. I have to ask you something, and I want you to think about it for a second. What does it mean to have a conversation? For us, it's sound waves traveling through the air, or light on a screen, or words on a page. It's something immediate, happening right here, right now. Now, look up at the night sky. Those pinpricks of light? They're not just silent, static ornaments. Every single one of them is talking. Shouting, whispering, singing the story of their birth, their life, and their death. But they're not using words. Their language is written in the very fabric of reality itself, in ripples of gravity, in ghostly particles that pass through you unnoticed, in colors of light our eyes can't even see. They've been having this universe-spanning conversation for billions of years. And for most of human history, we were sitting in the room, utterly deaf to it. Today, we're going to learn how to listen. We are going to tune our ears to the silent signals, how stars communicate across light years. We'll learn the dialects of exploding suns, the precise ticks of cosmic lighthouses, and even go hunting for the faintest whispers from the dawn of time. This is a story about how the universe talks, and how, piece by incredible piece, humanity is finally starting to understand. Before we dive into the cosmic static, if you're ready for a journey across the electromagnetic spectrum and the folds of space-time, do me a huge favor, smash that like button. It really helps the channel grow and tells YouTube that more people should join us for these deep dives. And of course, if you haven't already, subscribe and hit that notification bell. You won't want to miss a single episode as we decode the universe. And here's a fun little experiment for us. As you're watching this, I want you to comment down below with your location on Earth and the time you're watching. It's a small reminder that we're all on this little blue dot together, looking up at the same cosmic chatter, no matter where or when we are. Let's see how far and wide this conversation reaches. Alright. Headsets on. Volume up. Let's begin our listening session. Our first lesson in cosmic linguistics starts with the most familiar form of communication we know, light. But we have to immediately expand our definition far, far beyond what our human eyes can perceive. We need to talk about the electromagnetic spectrum. Think of it as the universe's grand radio, capable of broadcasting on an infinite number of stations, from the deep, booming bass of long radio waves to the piercing, high-energy screech of gamma rays. For most of history, we were only tuned into one, tiny, visible station. The story of us learning to listen on other bands is a story of curiosity and accident. In 1800, the astronomer William Herschel was passing sunlight through a prism, creating a rainbow, and measuring the temperature of each color. He found something astonishing. The hottest temperature wasn't in the violet or blue light, it was in the darkness beyond the red. He had discovered infrared radiation, invisible light that carries heat. A year later, Johann Ritter, experimenting at the other end of the rainbow, found chemical rays, beyond violet, that could trigger reactions. These were ultraviolet rays. The visible spectrum had borders, and we had just stepped beyond them. The real revolution came from a theorist, James Clerk Maxwell. In the 1860s, he united electricity and magnetism into a single, beautiful set of equations. These equations predicted waves of intertwined electric and magnetic fields traveling at a specific speed. When Maxwell calculated that speed, it was a number he recognized, the speed of light. His stunning conclusion was that light itself was an electromagnetic wave. But his math didn't stop there. It implied the possibility of an infinite variety of these waves, at all sorts of frequencies and wavelengths, all traveling at that universal speed limit. The entire electromagnetic spectrum was predicted on paper before we knew how to detect most of it. Heinrich Hertz proved Maxwell right in the 1880s. He built a circuit to generate and detect what we now call radio waves, showing they could be reflected and refracted just like light. Wilhelm Röntgen, in 1895, discovered X-rays by accident while experimenting with cathode ray tubes, finding a mysterious radiation that could pass through flesh but not bone. And the final piece, gamma rays, was identified in 1900 by Paul Villard studying radioactive radium. With that, the full scale of the cosmic broadcaster was laid out before us, from radio waves with wavelengths longer than mountains, to gamma rays with wavelengths smaller than an atomic nucleus. So, how do stars use this incredible bandwidth? They broadcast their entire life story. A calm, middle-aged star like our Sun chats mostly in visible light, infrared, and a bit of ultraviolet. But the drama happens at the extremes. When a star dies in a supernova, a cataclysmic explosion so bright it can outshine an entire galaxy, it doesn't just blast out visible light. That final, dying roar is a scream across the entire spectrum. In the initial shockwave, unimaginable energies are released, creating a firestorm of X-rays and gamma rays. These are the highest energy stations on the cosmic dial, carrying news of atomic nuclei being torn apart and particles accelerated to nearly the speed of light. The expanding shell of debris, the supernova remnant, then glows for thousands of years in radio waves, as high-energy electrons spiral in magnetic fields. By listening to all these channels, we don't just see an explosion, we understand its physics, its energy, and how it scatters newly forged elements like carbon, oxygen, and iron back into space to become building blocks for new stars, planets, and even life. But what about a more rhythmic signal? Imagine a metronome of unbelievable precision, ticking away in the void. That's a pulsar. A pulsar is a rapidly spinning, city-sized cinder called a neutron star, the crushed core left behind after a massive star goes supernova. To understand the pulsar, we have to witness the spectacularly violent death of its parent. We have to go back to the supernova. Picture a star, much more massive than our Sun, maybe 8, 10, or even 20 times heavier. For millions of years, it's been a grand cosmic factory, fusing elements in its core, hydrogen into helium, helium into carbon, and so on, each step releasing energy that pushes outward, holding the star up against the relentless inward crush of its own gravity. This balancing act is the story of a star's life. But the factory has one final, doomed product: iron. Fusing iron doesn't release energy, it consumes it. So, when the star's core finally becomes a ball of iron, the engine suddenly stalls. With no outward pressure from fusion, gravity wins, catastrophically and instantly. The core, which might be as big as Earth, collapses in on itself in less than a second. The force is so unimaginable that it smashes atoms together. Electrons are rammed into protons, and they merge to form neutrons, releasing a flood of ghostly particles called neutrinos in the process. What was once a complex mix of atomic nuclei becomes, almost entirely, a seething, ultra-dense ball of neutrons. This collapse is halted only by a bizarre quantum law, a rule called neutron degeneracy pressure. In simple terms, neutrons, like other subatomic particles, resist being packed into the same space. This resistance creates a final, desperate outward push. For a core of a certain mass, between about 1.4 and 2 to 3 times the mass of our Sun, this neutron pressure just barely balances the crushing weight of gravity. A neutron star is born in that precarious, perfect standoff. But the story isn't over. The rest of the star, the outer layers, are still falling inward at a quarter the speed of light, only to hit this newly forged, impenetrable neutron core and rebound in the most energetic explosion in the universe, a supernova. That's what we might see blazing across the galaxy, the outer layers being blasted away, creating beautiful, expanding nebulae like the Crab. And sitting at the very heart of that chaos is our newborn neutron star. Now, let's talk about why this thing is spinning so unbelievably fast. It's all thanks to a principle you might have seen if you've watched a figure skater perform a spin. When they start with their arms outstretched, they spin slowly. As they pull their arms tight to their body, they spin faster and faster. This is the conservation of angular momentum. The star that collapsed was already rotating, maybe slowly, like our Sun, which takes about a month to turn once. But when you take an object that was millions of kilometers across and crush it down to a sphere just 10 to 20 kilometers in diameter, the size of a small city, its rotation speeds up by a colossal amount. It's the ultimate cosmic pirouette. A star that rotated once a month can become a neutron star spinning hundreds of times per second. The current record holder, PSR J1748-2446 AD, spins 716 times every single second. Just try to comprehend that. An object with more mass than our Sun, completing a full rotation in less time than it takes you to blink. And then there's the magnetic field. If you thought the spin was extreme, wait for this. Stars have magnetic fields. Our Sun has one. When you crush that star down by a factor of 1,000,000, you're also squeezing those magnetic field lines together. The magnetic field strength skyrockets. A typical neutron star ends up with a magnetic field about 1,000,000,000,000 times stronger than Earth's. In some special cases, they become magnetars, with fields another 1,000 times stronger still, the most powerful magnets in the universe. These fields are so intense that they can literally distort the shape of atoms and have profound effects on the space around the star. This brings us to the pulsar's voice, its beam of radiation. The neutron star's insane magnetic field shapes its immediate environment into what's called a magnetosphere. Charged particles, electrons and their antimatter counterparts, positrons, get caught in this magnetic grip. They are accelerated to near light speeds along the curved magnetic field lines, particularly near the magnetic poles. This process generates intense beams of coherent radio waves, and sometimes visible light, X-rays, or gamma rays shooting out from the magnetic poles. It's not just random static, it's a focused, powerful signal, like the beam from a lighthouse. But here's the final piece of the puzzle that makes it a pulsar and not just a noisy neutron star. The magnetic poles are almost never aligned with the star's axis of rotation. Imagine a lighthouse where the light isn't on top of the tower, but stuck to its side. As the lighthouse, the neutron star, spins, the beam sweeps around in a great circle. For most places in the cosmos, that beam is just sweeping through empty darkness. But if you, an observer, happen to be sitting in the right spot, in the path of that sweeping beam, you'll see a brilliant flash every time it points at you. They're gone. They're gone. That flash is the pulse. The time between pulses is exactly the time it takes for the neutron star to spin once. So, when we detect a pulse every 1.337 seconds, like Jocelyn Bell first did, or every 0.0014 seconds for a millisecond pulsar, we are directly measuring the star's rotation period. Now, the discovery of that first signal is a story that wonderfully blends human curiosity, rigorous science, and a healthy dose of humor in the face of the unknown. In 1967, at the Mullard Radio Astronomy Observatory in Cambridge, a brilliant PhD student named Jocelyn Bell was meticulously analyzing miles of paper chart recordings from a new radio telescope she helped build. The telescope was designed to study the twinkling of distant galaxies, but Bell noticed something odd, a bit of scruff, as she called it, that appeared at the same spot in the sky every single day. This regularity ruled out terrestrial interference like TV signals or radar. It was coming from a fixed location among the stars. With a faster recorder, she and her supervisor Anthony Hewish resolved the scruff into a series of sharp, perfectly spaced pulses, 1.337 seconds apart. Nothing in known astronomy behaved like this. Pulsating stars existed, but their rhythms were minutes or days long, not precise, rapid ticks. The sheer regularity of it was unnerving. In a now famous moment of scientific caution mixed with playful speculation, they labeled the signal LGM1, Little Green Men 1. They had to seriously consider, just for a while, that they might have stumbled upon a beacon from an extraterrestrial civilization. As Bell herself later said, they didn't truly believe it, but they had no proof it was natural, and announcing a potential alien signal required immense responsibility. The LGM hypothesis was finally put to rest a few weeks later when Bell discovered a second, similar pulsating source in a completely different part of the sky. One alien beacon was a thrilling possibility. Two different ones in different constellations made it a natural phenomenon. They had found a new type of celestial object, the pulsar. Pulsar timing does more than test gravity. In 1992, astronomers discovered slight, periodic variations in the pulse timing from a pulsar named PSR B1257+12. The pattern revealed the gravitational tug of not one, but multiple planets orbiting it. These were the first planets ever discovered outside our solar system, exoplanets, long before the Kepler mission found thousands around Sun-like stars. They were found orbiting a stellar corpse, in a system bathed in intense radiation, proving that planets could form in the most unexpected places. The applications keep growing. Because pulsar signals travel vast distances to reach us, they pass through the interstellar medium, the thin gas and dust between stars. This material can scatter and delay the radio waves, causing the signal to twinkle, similar to how stars twinkle in our atmosphere. By studying this scintillation, astronomers can map this invisible interstellar material. It also poses a challenge for ultra-precise timing, because to use a pulsar as a clock, you need to account for every possible delay, even those caused by this interstellar twinkle. Research, like recent work from the SETI Institute tracking the long-term scintillation of a pulsar, helps astronomers calibrate these effects out, making the cosmic clocks even more precise. And this precision is the key to one of the most ambitious experiments in modern astronomy: pulsar timing arrays. Projects like NanoGrav in North America, which uses the immense Green Bank telescope, don't just watch one pulsar. They monitor an entire array of the most stable millisecond pulsars across the galaxy, some for over 15 years. The idea is to create a galaxy-scale gravitational wave detector. The gravitational waves we've detected with LIGO are like high-frequency chirps from stellar mass black holes colliding. But supermassive black holes at the centers of galaxies, orbiting each other for eons, should produce a constant, low-frequency hum, a gravitational wave background. As these waves wash over the galaxy, they would minutely stretch and squeeze the fabric of space between the pulsars and us. This would cause the incredibly regular pulses from all these distant clocks to arrive at Earth just a tiny bit early or late, in a correlated pattern across the whole array. Detecting that pattern is like sensing a barely perceptible swell in a vast cosmic ocean. It would allow us to listen to the chorus of supermassive black hole mergers throughout the universe and probe the universe in a way light alone never could. So, from a curious bit of scruff on a chart recorder, pulsars have become one of astronomy's most versatile tools. They are natural laboratories for extreme physics, proving grounds for gravity, signposts for the first alien worlds, probes of the interstellar medium, and the heart of a daring attempt to hear the fundamental hum of the cosmos. They remind us that sometimes the universe's most useful tools aren't things we build, but wonders we are lucky enough to discover, listen to, and learn from. So, we've learned to listen to the universe's light show and decode the rhythmic ticks of its most precise clocks. But now, let's prepare for something that challenges our very intuition. We're going to move beyond light and particles altogether. We're going to learn to feel the universe. Not with our hands, but with instruments so sensitive they can feel the stretching and squeezing of reality's canvas. We've been looking at the painting, now we're going to feel the canvas itself tremble. This brings us to our second, and perhaps most mind-bending, form of cosmic communication: gravitational waves. If the electromagnetic spectrum is the universe's radio, broadcasting on channels of light and color, then gravitational waves are its subsonic rumble, the vibrations in the very floorboards of reality. To understand this, we need to revisit a fundamental idea. We often think of space as a static stage and time as a steady ticker tape, on which events simply play out. But Albert Einstein's general theory of relativity, published in 1915, wove them together into a single, dynamic fabric, space-time. And mass, he said, doesn't just sit in this fabric, it warps it. Picture a heavy bowling ball placed on a taut, stretched rubber sheet. The sheet curves, creating a depression. A marble rolled nearby will spiral into that depression, not because of a mysterious force pulling it, but because it's simply following the curved path of the sheet. That's gravity. It's not a force that reaches out and grabs you, it's the geometry of the universe. You fall because you're following a straight line path through a curved reality. Now, here's the crucial part for our story: that curvature isn't static. If the bowling ball moves, if it jiggles or rolls, or, crucially, if two bowling balls spiral around each other, the deformations in the rubber sheet don't update everywhere instantly. The news of the new position travels outward as ripples. Those ripples in the fabric of space-time are gravitational waves. They are not ripples in space and time, they are ripples of space and time itself. As they pass, they literally stretch and squeeze the distances between points in space, and they do so at the speed of light. Think of them as traveling stretches and squeezes of the cosmos. Einstein himself predicted these waves in 1916. The mathematics of his beautiful theory demanded they exist. But for a century, they remained just that, a beautiful mathematical prediction. The reason? The effect is unimaginably, almost insultingly tiny. We're talking about the most violent events in the universe, black holes colliding with the energy of billions of suns, and by the time those ripples travel across the cosmic ocean to reach us, they have faded to the faintest of whispers. The stretching and squeezing from such an event would change the distance between objects by less than the width of a single atomic nucleus over a span of kilometers. Einstein himself was convinced it would never be possible to measure them. Detecting this seemed less like engineering and more like fantasy. The quest began with a physicist named Joseph Weber in the 1960s. He built the first detectors called Weber bars. These were massive aluminum cylinders, isolated from vibration, designed to ring like a bell if a gravitational wave passed through. For a while, he believed he had detected signals, but other groups couldn't reproduce his results. The consensus was that the bars just weren't sensitive enough. The field needed a new idea, a different way to measure the unimaginably small. That new idea came in the form of light and geometry. Instead of trying to make a single object ring, what if you used the constant speed of light as the universe's most perfect ruler? This is the principle behind a laser interferometer, and the most famous of these is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO's design is genius in its elegant simplicity. Imagine a capital letter, L, drawn on the ground, but each arm of that L is a perfectly straight, vacuum-sealed tube 4 kilometers long. At the corner sits a laser. Its beam is split, sending one half down one arm and the other half down the perpendicular arm. At the end of each arm hangs a mirror, suspended so delicately it's practically floating in free fall. The light beams hit these mirrors, bounce straight back, and recombine at the corner. Here's the magic trick. When the arms are exactly the same length, the returning light waves are perfectly aligned, but deliberately set up to cancel each other out, a process called destructive interference. The detector's output, in its perfect, quiet state, is darkness. Now, a gravitational wave passes through. Remember its nature, it stretches space in one direction and squeezes it in the perpendicular direction. So, as the wave passes, one of LIGO's 4-kilometer arms gets minutely longer, while the other gets minutely shorter. The distance the laser light travels in each arm changes by that ludicrously small amount, a shift of just 1/10,000th the width of a proton. This tiny change means the light waves no longer meet perfectly out of sync. They no longer cancel out completely. A tiny, specific flicker of light appears in the darkness. That flicker is the signature. It is space-time itself ringing like a bell, and LIGO is the stethoscope listening to its heartbeat. Building such an instrument wasn't just an engineering challenge, it was a war against noise. Seismic vibrations from distant trucks, the microscopic thermal jiggling of atoms in the mirrors, even the constant random spatter of photons from the laser itself, a quantum effect called shot noise, could all masquerade as a signal. To have any hope, LIGO needed to be not one, but two identical detectors, separated by 1,865 miles in Livingston, Louisiana, and Hanford, Washington. A true gravitational wave, traveling at light speed, would hit both detectors within a tiny, predictable window of time. Any local vibration would only affect one. This cross-check was essential. The story of LIGO is also a story of decades of human perseverance. Key figures like Rainer Weiss of MIT, who worked out the fundamental blueprints for the interferometer and identified the major sources of noise, and Kip Thorne of Caltech, who championed the theoretical vision and dreamed of the astrophysical discoveries to come, kept the dream alive through years of skepticism. Barry Barish later provided the crucial leadership to scale the project from a prototype into a big, disciplined, international science collaboration. For their decisive contributions, These three were awarded the Nobel Prize in Physics in 2017. And then, after decades of work and a major upgrade to become Advanced LIGO, the impossible happened. On September 14, 2015, at 5:51 a.m. Eastern Time, a gravitational wave swept through the Earth. In Livingston, Louisiana, the signal arrived. 7 milliseconds later, as expected for a wave traveling at light speed, it arrived in Hanford, Washington. The computers registered the telltale flicker. The signal was clean. It was strong. It matched the theoretical prediction perfectly. It was a chirp, a rapid rise in frequency and amplitude that ended abruptly. Scientists decoded that chirp. It was the sound of two black holes, each about 30 times the mass of our Sun, performing their final, fatal dance about 1.3 billion light-years away. For eons, they had orbited each other, radiating away energy in gravitational waves, spiraling closer. In their last frantic moments, they orbited at nearly half the speed of light before finally merging into one larger black hole. In a fraction of a second, an amount of energy equivalent to 3 times the mass of our Sun was converted into pure gravitational wave energy and blasted across the universe. That energy, after traveling for 1.3 billion years, gently rocked LIGO's mirrors. Humanity had directly detected gravitational waves. Since that first historic chirp, the LIGO-Virgo-Cagra network has been listening to a cosmic symphony of collisions. We've cataloged dozens of mergers, mostly pairs of black holes. But then, in August 2017, came a different kind of event. The detectors picked up a gravitational wave signal that lasted for over 100 seconds, much longer than the fraction of a second black hole mergers. This was the signature of less massive, denser objects, 2 neutron stars spiraling together. Crucially, within seconds of the gravitational wave detection, space telescopes around the world detected a flash of gamma rays from the same patch of sky. Then optical telescopes found a new, bright point of light, a kilonova, the glowing debris from the collision. For the first time, we had seen the same cosmic catastrophe with 2 completely different senses. We heard it in spacetime and saw it in light. This was the dawn of multi-messenger astronomy, and it confirmed that the heavy elements in our universe, like gold and platinum, are forged in these incredible collisions. The network continued to fill in the family album. In 2020, it found the missing link, the collision of a black hole with a neutron star. They detected 2 such events just 10 days apart. In the first, a black hole about 9 times the Sun's mass found a neutron star companion of 1.9 solar masses. In the second, a 6 solar mass black hole met a 1.5 solar mass neutron star. Scientists believe in both cases the black hole swallowed the neutron star whole, like a cosmic gulp. With no stellar debris flying out, there was no bright light show. To any telescope, it was a completely dark, silent merger. But gravitational waves don't care about light. They gave us a front-row seat to this invisible, monumental consumption. This is the profound power of gravitational wave astronomy. It lets us hear the dark universe. We can now listen to the stately, inspiraling dance of binary stars, white dwarfs or neutron stars orbiting for millions of years, whose gradual inspiral creates a continuous, detectable hum at frequencies too low for LIGO. To catch these, we use the galaxy itself as a detector through pulsar timing arrays. By monitoring the incredibly regular ticks from a network of millisecond pulsars across the Milky Way for years, astronomers look for correlated delays in their arrival times caused by the gentle stretching of spacetime by long-wavelength gravitational waves. In 2023, several international teams announced strong evidence for a background hum of these waves, likely from the combined din of millions of pairs of supermassive black holes orbiting at the hearts of distant galaxies. We are hearing the universe's bass note. And we are hunting for the faintest whispers of all primordial gravitational waves. These would be ripples from the violent birth pangs of the universe itself, generated in the first fraction of a second after the Big Bang, when the cosmos expanded faster than light in a process called inflation. Imprinted on the cosmos like a fossil, detecting them would be like listening to the universe's first cry. Some experiments search for the unique twisted pattern called B-mode polarization. These waves would have left in the oldest light in the universe, the cosmic microwave background. Others dream of future space-based observatories, like LISA, which would operate in the quiet of space, free from Earth's tremors, to listen for waves from the earliest supermassive black holes. From a theoretical curiosity that even Einstein doubted could be measured, gravitational waves have become a fundamental new sense for humanity. They have confirmed the last untested prediction of general relativity, revealed a hidden population of black holes, shown us how gold is made, and begun to tune our ears to the low hum of cosmic history. We are no longer just stargazers. We are now, truly, listeners in the grand concert hall of spacetime. But while gravitational waves let us feel the structure of spacetime, there's another messenger that lets us peer directly into the nuclear furnaces at the heart of stars. A messenger so ghostly that it makes light seem slow and clumsy. That messenger is the neutrino. Neutrinos are, frankly, absurd particles. They are elementary particles, like electrons, but with a crucial difference: they barely interact with anything. They have no electric charge and only feel the weak nuclear force and gravity. A neutrino can pass through a light year of solid lead without breaking a sweat. And they are being produced in staggering numbers. Right now, as you watch this, billions of neutrinos from the sun are streaming through your body every second. They are the byproducts of the nuclear fusion that powers our star, the direct signal of protons fusing into helium deep in the solar core. The light we see from the sun takes over 100,000 years to random walk its way out from the core. Neutrinos, indifferent to the dense plasma, zip out in just over 2 seconds. They are a live broadcast from the sun's engine room. Now, scale that up to a star's death. In a core collapse supernova, the processes are unimaginably more intense. As the iron core collapses, protons and electrons are crushed together to form neutrons, releasing a flood of electron neutrinos in what's called the neutronization burst. In the hellish conditions that follow, all flavors of neutrinos and antineutrinos are produced in staggering numbers, about 10 to the power of 58 of them, carrying away 99% of the star's gravitational binding energy in a burst lasting tens of seconds. This makes a supernova a blinding flash of neutrinos. And here's the incredible part: those neutrinos leave before the light does. The visible supernova explosion is the shockwave blasting through the star's outer layers, which takes hours to reach the surface. The neutrinos, however, escape from the collapsing core almost instantly. This means the supernova neutrino signal is an early warning system. If a star in our galaxy were to go supernova tomorrow, underground detectors like Super Cameo Candy in Japan or IceCube at the South Pole would register a sudden spike of neutrinos, hours before any telescopes saw the first hint of light in the sky. We've only seen this happen once, with supernova 1987A, which exploded in a nearby dwarf galaxy. On February 23, 1987, several detectors on Earth registered a handful of neutrinos, 24 in total, over a span of 13 seconds. Hours later, the light arrived. Those 24 ghostly particles confirmed our theories about stellar death and opened a new window into the most violent events. Future observatories, like the planned Hypercameo Candy, aimed to be so sensitive they could detect thousands of neutrinos from a similar event, giving us a detailed heartbeat monitor of a star's final moments. They could even peer into events that are completely shrouded in dust or are otherwise invisible, like the formation of a black hole, where the neutrino signal might be the only message that escapes. So far, we've talked about signals born from pure physics and raw energy. But the universe also communicates through chemistry. It leaves fingerprints, signatures in the very stuff that makes up everything. This is the chemical language of the cosmos. It starts in vast, cold clouds of gas and dust called molecular clouds or stellar nurseries. These are the cradles where new stars are born. These clouds aren't uniform. They're laced with complex molecules: water, ammonia, formaldehyde, even simple sugars. The specific mix of molecules acts as a chemical fingerprint of the environment, telling us about the temperature, density, and history of the cloud. When a new star ignites within, its radiation and stellar wind begin to cook and blow away this natal cloud, creating a rich chemical soup. By studying the light from these regions at different wavelengths, especially radio and infrared, which can penetrate the dust, we can read the recipe for star formation. Once a star is shining, we can decode its personal biography through spectroscopy. This is our most powerful tool for stellar conversation. When a star's light passes through a prism or a spectrograph, it's spread out into a rainbow. But that rainbow isn't smooth. It's crossed by dark lines, absorption lines, and sometimes bright lines, emission lines. These lines are the barcodes of the elements. Every atom and molecule absorb or emits light at very specific, unique wavelengths. By reading these barcodes in starlight, astronomers can tell what the star is made of, its composition of hydrogen, helium, oxygen, iron, and more. They can measure its temperature. Hotter stars have different lines than cooler ones, its density, its magnetic field, and even its motion. The Doppler shift of these lines tells us if the star is moving toward us, blue shift, or away from us, redshift, and how fast. Now, apply this genius technique not just to stars, but to the thin halo of gas around a distant planet. This is the cutting edge, the search for biosignatures on exoplanets. When an exoplanet passes in front of its host star, a tiny fraction of the star's light filters through the planet's atmosphere. Different molecules in that atmosphere absorb specific colors. By analyzing this filtered light with exquisite precision, we can, in theory, read the planet's atmospheric composition. The Holy Grail is finding a combination of gases that is hard to explain without life. On Earth, the simultaneous presence of abundant oxygen, O2, and methane, CH4, is a classic biosignature, as they react quickly and would neutralize each other without constant biological replenishment. Oxygen itself, especially at high abundance, has long been considered a strong sign of life, as it is the waste product of oxygenic photosynthesis. But the cosmic conversation is never simple. Scientists have discovered false positives, planetary processes that could build up oxygen without life, such as the photochemical breakup of water vapor on extremely hot planets, or a runaway greenhouse effect. And there are false negatives. A planet could have life like early Earth's for billions of years without building up significant atmospheric oxygen. So, the hunt isn't for a single gas, but for a context. Is the planet in its star's habitable zone? Does it have water? Does its atmosphere show a complex chemical disequilibrium? Finding the right combination is like listening for a specific, meaningful sentence in a noisy room full of random shouts. It's the ultimate act of cosmic eavesdropping, trying to hear the faint signal that whispers, "You are not alone." So, we've traveled a long way together on this journey of cosmic listening. We've tuned our ears to the scream of light across the spectrum, felt the space-time ripples from black holes colliding a billion light-years away, and even learned to catch the ghostly neutrinos that stream from the hearts of stars. We've become fluent, in a sense, in the known languages of the universe. But what if we've only learned the local dialects? What if, while we've been so focused on understanding the conversation in the room, there are entire, parallel conversations happening in other rooms, rooms whose doors we haven't found, whose very architecture we can't yet perceive? Our final chapter ventures into the realm of the speculative, the theoretical, and the profoundly unknown. This is the frontier of our listening post, where we ask, what if the universe is talking in ways we haven't even conceived yet? First, let's confront the universe's biggest secret, the elephant in the cosmic room, dark matter. We know it's there. We can feel its gravitational hand shaping everything. It guides the majestic swirl of galaxies, holds clusters of galaxies together, and bends the very path of light itself. We know it makes up about 85% of all the matter in the universe. That's a stunning fact to sit with. Everything we can see, every star, planet, nebula, and you and me, is just the cosmic icing on an invisible cake. But we have no idea what it is. It's dark because it doesn't play by the rules of our electromagnetic world. It doesn't emit, absorb, or reflect a single photon of light. It's completely transparent to our entire suite of telescopes. It is, for all our primary senses, not there. So, how do we hunt for something that refuses to be seen? We build traps. Incredibly sensitive traps deep underground, shielded from the cacophony of cosmic rays and everyday radiation. One of the most sensitive of these is the LUX Zeppelin, or LZ, experiment. Picture this: nearly a mile beneath the Black Hills of South Dakota, in the quiet, dark caverns of the Sanford Underground Research Facility, sits a giant tank holding 10 tons of ultra-pure, liquid xenon. It's kept at cryogenic temperatures, and it's watched by an array of incredibly sensitive light sensors. The idea is beautiful in its simplicity. If dark matter is made of particles, and one of the leading candidates are things called weakly interacting massive particles, or WIMPs, then one of these WIMPs might, very rarely, bump into the nucleus of a xenon atom. If that happens, the xenon atom would recoil, like a billiard ball getting struck, and release a tiny flash of light and a few electrons. The sensors would see that. Scientists have spent years collecting data, creating the cleanest, quietest environment possible to listen for that 1 in a trillion whisper of a bump. In their latest analysis of over 400 days of data, they've pushed sensitivity to new extremes, looking for lighter WIMPs than ever before. They haven't found a definitive signal yet, but that's science. Each time they don't find it, they draw a line on the map of possibilities and say, "It's not here." They are meticulously ruling out what dark matter is not, which is a crucial step toward finding out what it is. But here's a fascinating twist in the hunt. The LZ detector is now so sensitive that it's starting to hear something else: the faint pitter-patter of neutrinos from the Sun, specifically boron-8 solar neutrinos, produced in the Sun's core. This is a milestone, proving the detector works phenomenally well. But these neutrinos create a background hum, a kind of neutrino fog. For scientists looking for the faintest dark matter signals, this fog is a new challenge to peer through. It's a reminder that the universe is layered, and listening for one secret often means learning to filter out the whispers of another. Now, some scientists are looking for dark matter in other, more indirect ways. What if dark matter particles, very rarely, annihilate each other when they collide? Some theories suggest such a collision could produce a burst of gamma rays. In 2024, a Japanese astrophysicist, Tomonori Tatani, published a study suggesting he may have seen exactly this: a halo of gamma rays near the center of our Milky Way, with a pattern and energy signature that didn't match any known object like a pulsar or black hole. He cautiously proposed it could be the first glimpse of dark matter annihilation. The scientific community, rightly, met this extraordinary claim with healthy skepticism. Gamma rays come from many violent processes, and the center of our galaxy is a messy, complex place. As one scientist not involved in the study put it, "We don't even know all the things that can produce gamma rays in the universe." This is the cutting edge, a tantalizing hint, a possible signal, followed by years of painstaking work by other teams to confirm or refute it. The hunt is alive. But let's get truly speculative with dark matter. Could it communicate with itself? We feel its gravity, which is how it talks to us, or rather, how it pushes us around. But what if within its own shadow realm, dark matter particles talk to each other via their own forces? Physicists have theorized about dark photons or a dark force. Imagine a parallel universe of dark matter, with its own rich physics and interactions, layered right on top of our own. Galaxies would have a bright, luminous skeleton of stars and gas that we see, and within it, a more massive, intricate skeleton of dark matter, buzzing with its own unseen activity. They could be colliding, forming structures, even harboring dark stars powered by dark energy processes we can't fathom. We would be utterly blind to it, except for the subtle gravitational tugs we feel. It's a humbling thought: we might only ever be indirect eavesdroppers on a vast, hidden conversation. From the hidden, let's move to the primordial, to relics from the universe's first moments. Enter the mind-bending concept of cosmic strings. These aren't strings like on a guitar. They are theoretical, one-dimensional defects in space-time itself. Think of the early universe as a state of pure, symmetric energy. As it expanded and cooled incredibly rapidly, it underwent phase transitions, like steam condensing into water, or water freezing into ice. When water freezes, sometimes the ice forms with cracks or imperfections. Cosmic strings are like cracks in the fabric of reality, frozen into the cosmos when it was a fraction of a second old. If they exist, they are almost unimaginable objects. A filament thinner than a proton, but with the mass of a mountain range packed into every inch. They could stretch across light years, and they would be under immense tension. They could vibrate, or worse, snap. And when something with that much mass energy vibrates or breaks, it would send a tsunami of gravitational waves rippling through the cosmos. These wouldn't be the chirps from black holes LIGO hears. They'd be a sharp, singular crack in spacetime, a monumentally powerful burst. Or they might accelerate particles to insane energies, creating unexplained cosmic rays. Finding evidence of a cosmic string would be like uncovering a fossil from the universe's first trillionth of a second. It would be a direct telegram from the instant when the very laws of physics as we know them were setting into place. And this, of course, brings us to the question that has haunted our species since we first looked up with wonder and fear. Are we truly alone? For decades, SETI, the search for extraterrestrial intelligence, has been the organized effort to listen for a deliberate hello. They've mostly tuned their radio telescopes, listening for narrowband signals, the kind our own technology produces, that stand out against the natural radio noise of the cosmos. What if an advanced civilization isn't broadcasting a greeting to the void? What if they're just talking to each other? We don't beam powerful hello Earth messages into space. We use directed signals for satellite TV, radar, and communication between spacecraft. A 2024 study picked up on this idea, suggesting we might eavesdrop on such local communications. Imagine two exoplanets orbiting the same star. From our vantage point, one might periodically pass behind the other. If the hidden planet has a civilization beaming a signal to it, say, a focused laser or radio beam, some of that signal could leak around the edges of the foreground planet. For a brief moment, we might catch a whisper of an internal conversation, a narrow band signal that winks on and off in sync with the planetary orbits. It's a clever idea, searching not for a message for us, but for the spillover of messages meant for them. Others speculate a truly advanced society might ditch electromagnetic waves altogether. Why use light or radio, which can be scattered, absorbed, and distorted by interstellar dust and plasma? Why not use gravitational waves? They travel cleanly through everything, suffering almost no interference. A civilization that could generate controlled gravitational waves could have a pristine, ultra-secure galactic communication network. The problem for us, as you noted, is that with our current science, a perfectly engineered gravitational wave signal might be indistinguishable from the natural chirp of two merging neutron stars. We'd hear it, celebrate a new astrophysical discovery, and never know we were overhearing a phone call. This leads to the most profound and humbling possibility of all, that we are simply not equipped to hear the conversation yet. Our technology, our science, our very senses and brains, are the products of evolution on one planet, tuned to a very narrow band of reality. We see a thin slice of the electromagnetic spectrum. We hear a limited range of vibrations in air. This is our umwelt, our perceived world. An intelligence a million years more advanced might have a completely different umwelt. They might perceive and manipulate reality in ways we can't yet dream of. Their internet might be a network of quantum-entangled particles, allowing instant communication across the galaxy, utterly invisible to us. They might broadcast by subtly modulating dark matter fields, using the very fabric of the shadow universe as their medium. Or they might use a physics we haven't discovered yet, a fundamental interaction that doesn't touch normal matter in any way we can detect. Their signals might be all around us, a cacophony of cosmic conversation that we perceive as nothing more than the static of the cosmic microwave background, or the random noise in our particle detectors. We are like a person born deaf standing in the middle of a bustling city square. We see lips moving, gestures flying, but we hear only silence. We have no conception of the rich, layered world of sound. The greatest silent signal, the one that truly matters, might be the one we're still deaf to. Our journey as cosmic listeners have just begun. The most important chapter in the story of the universe's conversation may be the one we have yet to learn how to read. And so, our listening session comes to a close. We started by learning to see beyond the rainbow, to hear the whispers of light our eyes could not see. We learned to feel the stretching and squeezing of spacetime itself, to catch the ghostly neutrinos that tell tales from stellar cores. We learned to read the chemical poetry written in starlight and on distant worlds. And we dared to wonder about conversations happening in the dark, in the cracks of reality, or in languages of physics we have yet to learn. The universe is not silent. It is a symphony. A supernova's final chord, a pulsar's rhythmic beat, the low bass note of colliding black holes, the soft hiss of the cosmic microwave background, it's all there. For billions of years, the stars have been telling their stories. We, a young species on a pale blue dot, have just begun to prick up our ears. The conversation is endless. And we are finally starting to listen. If this journey through the silent signals of the cosmos lit up your curiosity like a supernova, please let me know by giving this video a thumbs up. It means the world to us. If you haven't already, subscribe to the channel and ring that notification bell. We have so many more cosmic mysteries to unravel together, from the quantum weirdness of black holes to the large-scale structure of everything. And remember, I asked you at the beginning to comment with your location and the time you're watching. It's a beautiful thing to think that while we're all scattered across this globe, under different skies and at different hours, we can still come together to try and understand the grand, shared sky above us. Let's see that community in the comments. Thank you so much for spending this time with me, for lending me your ears and your imagination. Wherever you are, whatever time it is for you, whether it's the middle of the day or deep in the quiet of the night, I hope you look up before you go. Remember, you're not just looking at points of light. You're looking at an ongoing, billion-year conversation. Take care, stay curious, and good night.